So in this week's lecture, we're going to cover polymers, which are used in a wide variety of biomaterial applications. In fact, polymers represent the largest class of materials used in medicine today. We're going to cover a basic overview of polymers. We're going to get into the molecular architecture, molecular weight, and chemical composition, and specifically those that directly affect the structure-property relationship of polymers. So ones that link the chemical properties with the physical properties on a macroscopic scale. In the second half of the lecture, we'll cover three specific polymers that are widely used in biomaterials, although it's certainly not an extensive list, and there are many polymers as we're going to learn about throughout the course. I was going to try and avoid the generic Webster's Dictionary defines polymer as, but I really think it's the best way to get into it. Polymer comes from the Greek root words poly, meaning many, and mer, meaning part. So polymers are just made up of repeating subunits that derive from monomers, the original mer part. In fact, the hallmark of polymers is their high molecular weight. So if you consider the molecular weight of something like water, which is only 18 Daltons, and then a typical polymer might be 200,000 Daltons. And it's this possibility to have thousands and thousands of repeating units that make it possible to have such a high molecular weight, something that would not be seen in nature with other kinds of materials. Now, the simplest way polymers can be organized is in a simple linear chain, just going in one direction, one after another. A more complex pattern might be in the form of a branch chain, where the backbone of a polymer might have reactive groups that can then further polymerize and go off in multiple directions as opposed to a single linear line. Even more complex patterns can emerge from the cross-linking of either branched or even linear polymer networks to form a network polymer. And it's this cross-linking of independently formed polymer chains that can form highly complex polymer networks. Furthermore, polymer chains don't need to consist of the same repeating unit, like in the case of a homopolymer. They could also consist of two separate linear chains that are bonded together in the form of a block copolymer, which have their own separate sections. A randomized copolymer, on the other hand, are ones that have different repeating subunits randomly mixed in with each other. Different subunits could still be mixed in with each other, but in a very organized alternating fashion, like in this ABA format. We could also have graph copolymers, which are different linear chains that are cross-linked on the backbone of one another. And note that all these structures can be further extrapolated when incorporating third polymer chains, fourth polymer chains, so the combinations are really limitless. Now, as I said before, polymers are created through the polymerization of low molecular weight parts called monomers. And it's the degree of polymerization that determines how many repeating units there are in a single molecule. So think of this as like the extent of a reaction. So you could either have a short reaction that just create a small polymer, or you could allow that reaction to continue and continue. And as long as you don't stop it, you can, in theory, make an infinitesimally large polymer. Although logistically and in practice, there are a lot of things that would prevent that from happening. Now, when we're trying to do this, we can never just focus and create one molecule per reaction, right? So we're always making millions and trillions of different molecules at a given time. And because we can't precisely control the degree of polymerization with each molecule, we're always going to have a heterogeneous mix of polymers with different molecular weights and different degrees of polymerization. So we need to characterize the molecular weight never of a single molecule, but of the entire heterogeneous mixture of those polymers. We do so by describing the average molecular weight. Except whenever we talk about an average, we have to consider what frame of reference we're using or how it's weighted. And polymer scientists use two ways to consider the average molecular weight and the frame of references. One is termed the number average molecular weight. The other is the weight average molecular weight. Number average, I think, is a little bit more simpler for people to interpret because it's more related to the typical mean or average that we've used since grade school. The weight average molecular weight is calculated using the square of the molecular weight in the numerator. So it's always more biased and heavily favored towards the larger molecules in a reaction, even if there are fewer. An analogy I like to use in this case is that if you have a mixture of balls consisting of 10 golf balls and one basketball, and someone asks you what's the average size of these, you would have to ask yourself how you account for the very large basketball as the outlier of the group. If you were to just add up all 11 balls and add up their diameters and divide it up by the number of balls, you would get a number very close to the golf ball because there's so many of them in comparison to basketball. However, if you were to factor in and weigh it towards the diameter of the balls and include that in the numerator, then you're going to see the effects of that basketball in the mix. And for whatever application, whatever reason is why you're counting these up, that might be necessary to take into account. And as you can see by the two equations, the weight average molecular weight, or the diameter of the basketball in the analogy, is going to always result in a larger number for the weight average as opposed to the number average. Then, to get a sense of the distribution of molecular weights in a given sample, or the heterogeneity of your molecular weights, you can calculate what's called the polydispersity index, which is the spread of the different polymerization degrees. And it's calculated using the weight average molecular weight divided by the number average molecular weight. And because the weight average is always going to be larger than the number average, the scale of this number goes from 1, indicating a completely uniform and homogeneous mixture of polymers that all have the same molecular weight, to potentially infinity if you have a large spread of molecular weights. Today, the most common way of measuring polymer molecular weights and the polydispersity is to use gel permeation chromatography, or GPC. This form of chromatography separates compounds by molecular weight so that large molecular weight compounds come out of a GPC column first and they get detected, and then smaller ones come out later and they get detected. The result of this is a curve like shown here on the slide, where you know the count of how many particles of a particular molecular weight come out because you compared it to some standards curve, and because you have the number of each size of compound that comes out, you can use those inputs of the two equations from the previous slides, and then also get the polydispersity. So now we've talked about the molecular weight and chain architecture of polymer. We want to start relating how these chemical features can make up the macromolecular behavior, like strength. Okay, because this is one of the key design features that we would need to take into account when making a biomaterial. If we were to make a bone cement, for instance, we have to ensure that the material is both strong enough to act as a cement, but not so brittle that it would just fail due to low fracture toughness. Much of this physical behavior is dependent on the physical state of polymers, which can be classified in two different ways. One would be an amorphous state, and then the opposite of that would be a crystalline or highly organized state. An amorphous polymer is one that has molecules found in unorganized, random orientations that are highly interpenetrated with neighboring molecules. An amorphous polymer can be further subcategorized into either a rubbery or a glassy state, depending on how much thermal energy it has. If an amorphous polymer has been melted to the point where it has enough thermal energy for rotations around single bonds to occur, so it makes it soft, flexible, and extendable, we would say that it's in the rubbery state. Below a certain temperature, the polymer lacks the ability to rotate around its single bonds. In this case, it forms a rigid and also stronger structure known as a glassy state. The temperature that divides these two is the glass transition temperature. Now, as your college students, and no doubt very familiar with ramen noodles, you're already very familiar with this transitioning pattern. At a low temperature below the glass transition temperature, these noodles are a solid brick, and while very strong, are also very brittle, so that you could actually very easily break them. However, when you heat them above their glass transition temperature, they turn back to a rubbery state, and they're very flexible, very soft. It's hard to break them in half unless you can really pull them and get a good grip on them. So I think this illustrates the behavior very well of the difference between a rubbery and a glass state. Now, the opposite of an amorphous structure, which again is an unorganized, random orientation of polymer structures, would be a crystalline state, where the polymers form rigid and very organized lattice structures. Now, in practice, it's very difficult and almost unfeasible to get an entire polymer structure into a crystalline state, and furthermore, many complex polymers only have the ability for some of their regions to form lattice structures while other areas can't. Therefore, we usually say that some polymers with organized structures are in a semi-crystalline state, where only portions of those polymers capable of forming the lattice structures are formed. Now, these crystalline regions can be broken down by heating the polymer above its crystalline melting point, Tm. Now, the Tm is always well above the glass transition temperature, so polymers can go through a variety of these temperature transition points, which progressively bring them into stronger and more organized patterns. Because of this, biomedical engineers are very interested in these temperature transition points, specifically how close they are to body temperature for those biomaterials that are going to interact with the body. The two most common ways of determining these temperature transition points are through differential scanning colorimetry, or DSC, and dynamic mechanical analysis, or DMA. In DSC, a similar polymer sample is heated or cooled at a constant temperature rate. The amount of heat supplied or removed is then recorded. And then the step change of the temperature of the sample versus the heat supplied can indicate whenever these transition points have occurred. So like in the graph shown below, we have the heat supply on the y-axis, the temperature on the x-axis, and we can see the various plateaus or step changes that indicate whenever one of these temperature transitions has occurred. The other method, dynamic mechanical analysis, I sometimes see dynamic thermal analysis as well, DTA, measures the mechanical stiffness or modulus of a polymer sample over a temperature range. When heating a semicrystalline polymer, the stiffness or modulus will first drop significantly, almost 3 orders of magnitude, first when reaching the glass transition temperature, and then finally the melting temperature that disrupts and gets rid of all the crystalline structures in that polymer, making it completely amorphous and rubbery again. Finally, the physical properties of a polymer may change over time, especially in the body, depending on whether or not the polymer is biodegradable or biostable. Now, which one of these cases we want depends on the application of that particular polymer. If we want a load-bearing implant that's meant to last for decades or for the lifetime of a patient, we want a biostable polymer that isn't going to degrade over time. However, if we want to engineer, say, a tissue scaffold that over time gets replaced by the healthy cells of the body during like a wound repair process, then we want something that is biodegradable, preferably on the same time length as the wound healing process. Now, the main type of polymer degradation occurs via hydrolysis, which is the breaking of bonds via water. The stability of that is dependent on two factors. The first being water absorption, was how readily water can interact and get to the polymer. And the second is the susceptibility of those various chain bonds to hydrolysis. Both of these stability factors can influence various polymers in different ways. For instance, nylon 6,6 somewhat has an ability to absorb water. It's not exactly a hydrophilic polymer, but it does allow water absorption. However, the amine bonds in nylon 6,6 have a very low susceptibility to hydrolysis. In fact, while they do hydrolyze, it occurs over such a long period of time that on a given lifetime of a patient, we would consider this polymer biostable. PLGA, on the other hand, polylactic co-glycolic acid, is made up of both hydrophilic glycolic monomers and then hydrophobic lactic acid monomers. And the degree of these can change the water absorption, but in general, most 50-50 random mixtures of PLGA have a relatively low water absorption rates, but because their susceptibility of hydrolysis is on the medium or actually relatively high scale, these can be considered biodegradable over the lifetime of a patient. So PLA could, for instance, last a few years, maybe not for load-bearing applications, whereas PGA polymers that are only made up of the more hydrophilic glycolic acid monomer would degrade very rapidly. And a lot of these components can be used in sutures or other applications where we want the polymer to degrade within a very short time frame. On the other hand, PET has some of the same ester bonds that are found in PGA and PLGA. Despite this, however, the hydrophobic nature of the polymer and also the fact that it's always found in a highly crystalline state makes it so not susceptible to hydrolysis that's considered stable. And that's it for this week's lecture. Thanks.